Hi folks, this is a video to help you understand your Y-DNA results and also the reasons behind grouping people together. Now this video is mainly aimed at project administrators who are running surname projects, but it really is suitable for anybody who is in a surname project and would like to know a little bit more about why they are grouped in a particular way. So first of all, understanding your Y-DNA results, and we'll be looking at two major pages, your own results page and the gap pages, which are pages that are only seen by project administrators. Here is the Y chromosome, and if we unravel it, we'll see that we have the classical double helix discovered by Watson and Crick back in 1953. And if we stretch that out, it has two strands, like the rungs of like the two sides of a ladder, with these letters forming the rungs of the ladder all the way along its length. And these letters are the nucleotide bases G, C, A, and T: guanine, cytosine, adenine, and thymine. G always binds with C, A always binds with T. The curvy ones, curvy letters bind with each other, the straight-edged letters bind with each other, and that is always the way, which basically means that one strand down here is exactly the mirror image of the other strand lying above. Now, there are two types of DNA markers. The first one is the short tandem repeat. The second one is the single nucleotide polymorphism. STR is the abbreviation for short tandem repeat, and you can see here that it is consists of a sequence of bases TAC, TAC, TAC. That's repeated 3 times, and therefore the short tandem repeat value for this particular marker is 3. The single nucleotide polymorphism, on the other hand, is merely the substitution of a single base with some other base. So this one might have been a G in a previous existence, but as it was passed down from father to son, it got changed to an A. So those are the two types of DNA markers. Now, short tandem repeats, let's take a closer look at them, and then the single nucleotide polymorphism, of course, is just a single substitution. But these are some examples of STR markers, and they're all given a different name. It has a certain repeat type. Tetra means that there are 4 bases repeated. Here is the repeat motif. In this particular case, let's look at this one here, DIS 458. This particular case, it's GAAA, and that's repeated n number of times, the average for n being 17. So it would be GAAA, GAAA, GAAA 17 times, and the value for this marker, 458, is therefore 17. You see it here in the distribution of the marker frequencies for this particular marker, and you can see that 17 is the average number, with most people having a value of 17. 32% in fact of people have a value of 17 for this marker 458. But if you look up here, the repeat number can go down as low as 10, but that's only shared by 0.003% of the population, and it can go up as high as 23. 0.003% of the population. This is very, very useful when we're looking for rare marker values. So the extremes of this distribution, we will find rare marker values, and we'll be looking at that a little bit later on. Now, these are the DNA results page for the individual person. These are my results. You can see my name and kit number up there. These are my dad's, actually. That's my haplogroup assignment, the various other parts. It's very important, if you want to understand your results, to become familiar with all of these pages on your personal website, courtesy of Family Tree DNA. The most important ones that I use are my matches page and also the haplotree and SNPs page. So let's look at the matches page first. And here we have matches. First of all, it calculates them at the 67 marker level. You can change the marker level by clicking here and then clicking Run Report. If you want to increase the number of matches per page, you just click here and choose 50, 100, 500, 1000, whatever you prefer. In the first column we have genetic distance. That's the distance away, the number of steps away from an exact match. So the genetic distance here is 2 out of 67. In other words, it's 2 steps away from an exact match between my father and this particular individual here. And 3 steps here, 6 steps here, and so on for each of these individuals. Then in this column here we just have a list of the different tests that each of these individuals have actually taken. This one here has taken the Y-DNA 111 test and also Family Finder. This is the most important column here, the most distant ancestor. And the way I like it filled out is this one here. Thomas Gleason, 1822 to 1887, Boher Lahan, Kilmakill. The reason why is that the location is probably the most important aspect of information in this particular page, because it will help you decide whether or not this person's most distant known ancestor actually comes from the same area as yours. So I would encourage everybody to fill in the birth location as well as the name of their most distant known ancestor. That is the most important piece of information. And the birth year then would be the third most important piece of information in that particular line. The trouble is, of course, there is a limit on the amount of characters that you can put in this particular field when you're filling it in, and it would be nice if there were 100 characters instead of, I think it's just 50 at the moment. That would let people put in more information. This is very important because when we come to look at the surname projects, this is the information that is publicly displayed. This is the information that will help you connect with matches. Then we have the haplogroup column here, the terminal SNP column here, and the match date. We'll be looking at the Y-DNA haplogroup column here because it contains all of the SNPs. The terminal SNP column does not necessarily contain all of the SNPs because they are predicted rather than certified by single SNP testing or any other type of SNP testing. And those are the number of records in the database as of May of this year. Now, this is what the Surname Project homepage looks like, and here we have the kit numbers of the individuals, their names, the paternal ancestor's name, most distant ancestor's name, the haplogroup, and then all of the STR markers along a row with the values for each of those markers in the rows below them. I like to think of it as the Y-DNA chromosomes of each of these people here stacked up like a set of pancakes, if you like, but all aligned so that you can see the values for their markers in a row. It also is able to show up where these people differ from what's called the modal haplotype, which is this line up here, the mode. This is the most frequent occurrence of each of the values in the column below. So here it's 29, for example, even though there's some 30s down there. And these colored squares indicate that there is or has been a mutation away from the modal value for this particular group being lineage 1. Similarly down here, lineage 2 will have its own modal haplotype, and these colored squares represent the number of steps away from the modal haplotype for each of these individuals. So that's the family tree DNA way of displaying the surname projects, but I prefer the World Family Network way of displaying it. And here is the WFN version of the Gleason DNA project results. Lineage 1 again up here, lineage 2 down here, and the important thing I want to draw your attention to is this wonderful colored pattern that emerges. You can see it's very, very clearly distinct from lineage 2. They've got two very, very different colored patterns, and if we bring in lineage 3, again a very, very distinctive colored pattern. And the reason for this is that the colored squares here represent steps away not from the modal haplotype for the group, but the modal haplotype for the subclade of the haplogroup, and in this case it's haplogroup OR1B1 in all cases, which is one of the most common in Western Europe. So that's a very nice way of displaying the results for the Gleason Surname DNA project on World Families Network. Now, If you're an administrator, you will need to become familiar with your administration pages, and there's various ones. You really just have to click through them. The one that I use most commonly under member reports or member information. That would be the most common one that I use. Under genetic reports, I would look at Y-DNA results colorized most frequently, followed by Y-DNA genetic distance. Under project administration, I would look at member subgrouping for grouping new members together, and that would be the main page that I would look at there, perhaps join authorization as well. And you can click through the other ones. My settings is probably an important one to control the amount of email you get from the project. I don't like being notified of 12 marker matches, so I've turned that particular one off. So now we come to the hub of the presentation, which is why do you group people together? And the answer is because different pieces of evidence point to the probability that they are all closely related. So we're going to look at these different pieces of evidence, and the key word here is probability. Nothing is 100% certain in genealogy, including genetic genealogy. And when I talk about probability, I'm talking about anywhere from 60% up to 99.9%. So my criteria for grouping people into my projects, and I run the Farrell Project, the Gleason Project along with Judy Klassen-Gleason, my co-admin, and the Spearn DNA Project. So my particular criteria for grouping, which are based purely on my own personal experience, particularly of doing the Farrell Project, and you'll see a nice blog on that at that web link below. But I've developed this idea and refined it, I must say, over the last couple of years, and I've no doubt that if you were to watch an update of this presentation in 1 or 2 years' time, it would be slightly different and my opinion would be slightly refined as well. But here is what I've come up with. Allocation of a particular member to a specific genetic family within a project is based on the presence of some or all of the following criteria, and these can be considered markers of potential relatedness, MPRs. And the more markers that are present, the more likely that there is a real relationship between those members in that genetic group, and I've put inverted commas here, within the last 700 years or so. One also hears the term within a genealogical time frame. And of course, this is more applicable to those people who have surnames that are inherited. And in Ireland, the system of inherited surnames has been around for about 1,000 years. In other places, it's been around for about 700 years. So I'm choosing this arbitrary figure of 700 years to be the meaningful threshold for considering matches on the Y-DNA. So these markers of potential relatedness, these criteria, consist of both traditional genealogical indicators as well as genetic indicators. And the traditional ones are in blue, the genetic ones are in red. So for example, here is my current list of markers of potential relatedness. It was only 8 markers 2 years ago, but I've increased it to 10 markers in the interim. The first marker is a traditional genealogical marker. The member has the same surname. So if a new member is joining a project and he has the same surname as somebody else in the project, well then that's a potential marker that they're possibly related. That stands to reason, and there's nothing genetic about that, it's just pure genealogy. The second one, the genetic distance between 2 members, indicates a close or very close relationship, and we'll look at that. The TIP24 score is greater than 80%. Compared to the group modal haplotype. We'll take a look at that as well. There is a clear genetic distance demarcation between project members within a specific genetic clusters and project members outside of that particular genetic cluster, and we'll have a look at that as well. The presence of rare marker values among genetic group members. Number 6, SNP predictions are consistent, and we will take a close look at what I term matches terminal SNP analysis. And that is a new technique that has only really become possible in the last 2 years since the availability of large numbers of people doing SNP testing. And this is a new type of technique that I'm finding very, very useful for grouping people into specific genetic clusters within a surname project. So we'll take a look at that later on as well. SNP testing is consistent among the members of the particular group. The same surname variant is predominant in a genetic group. The same most distant known ancestor location is present in the particular genetic group. And lastly, the same MDKA is present in the particular genetic group. So first of all, just to look at the public pages, we have the first 12 markers, then the next up to 25, and then up to 37. So there's 3 panels. And then we have these mutations occurring here, appearing as either pink or blue, blue being a downward mutation, pink being an upward mutation. And the fast mutating markers are all indicated by the maroon or wine-coloured, the dark red-coloured markers at the menu at the top. The minimum, maximum and mode are recorded here. So in a group, once there are 3 or 4 people in a group, it's possible to calculate the minimum number, the maximum number, and the modal value, the most frequent occurrence. So for example, there are no mutations here, so the modal value is going to be the same as the value for all of these individual members going down here. But if we come up to here where there's a few mutations, we can see that the modal value is 33 to 41, but it varies 33 to 40, 33 to 42, 34 to 41, 34 to 41. So it does vary a lot, but the overall most frequent value in this group is 33 for the left-hand column and 41 for the right-hand column. So that is the modal value. And mutations are highlighted as distance from the mode. That's just some definitions to distinguish the mean value, which is the average value, the median value, which is the value in the middle of a range of numbers, and the modal value, the most frequent value. So that's just to differentiate mean from median from mode. And the modal haplotype is likely to be the closest to the genetic signature of the common ancestor, ? Previously there was no question mark. But in the course of the last 2 years, I've come to question that, and I think now this is probably not the case, because especially if you go back a long, long way, 700 years ago, there is a great probability that the genetic signature of the descendants of a particular ancestor will be skewed in one way or another. And therefore, I think the modal haplotype for a particular genetic group will be close to that of an ancestor, of the founding ancestor for that group, but not necessarily exactly the same. Okay, so the ancestral modal haplotype is a little bit of a misnomer these days, and that's why I will use the term modal haplotype rather than ancestral modal haplotype. Always compare new members of your project to the member in your genetic group closest to the modal haplotype. Again, a question mark. I would say yes, as a starting point, this is a great idea. Compare any new members joining your surname project to the member within a specific genetic group that is closest to the modal haplotype for that group. But there are caveats with this, because the person with the modal haplotype at the beginning, when you start a group and there's maybe 3 or 4 people in it, those 3 or 4 people may all have tested from the same family or may be closely related to each other. And they actually may be sitting on a distant branch of the particular tree associated with your surname. So if you imagine your surname has a founding father, an original ancestor, and of all his descendants, the particular people that have tested in the project might be sitting on a quite remote branch of the tree. And therefore, the modal haplotype for the group will actually be the modal haplotype of those people on that remote branch. So I would say in the initial stages of your project, there's no harm comparing people to the modal haplotype of this distant branch. But I think over time, what will happen as you get more members, the modal haplotype for the group will start moving away from that distant branch and more towards the genetic signature of what was the common ancestor to the group. So that's just a little word of caution about modal haplotype and comparing people to the modal haplotype. Good to start off with, but you may wish to modify that as your project proceeds. Here is the genetic distance and the match thresholds for declaring a match. So these are in the yellow boxes. The number of markers tested is 12, 25, 37, 67, 111, and the threshold for declaring a match, and for that match appearing in your project members' list of matches on their Y-DNA Matches page, is 1 out of 12 for a distance of up to 1, 0 or 1 for 12 markers, 1 only if the person matches people in other projects, otherwise it's 0. So if they're not in any projects, then it'll be 0 out of 12. For the 25 marker matches, it's 0 to 2 out of 25, 0 to 4 out of 37, 0 to 7 out of 67, and 0 to 10 out of 111. But if you look at the privacy policy page on Family Tree DNA, it defines the relationship for each of these values in a not very consistent way, and in fact at the threshold of 10 out of 111 it actually says that you're not related. So there is some inconsistency there. To remember the threshold, just apply the rule of 10%. The threshold for declaring a match is roughly 10% of the number of markers at that level. So 2 out of 25, 4 out of 37, 7 out of 67, and roughly about 10 out of 111. So just a nice rule of thumb. I suggested an approach 2 years ago to use genetic distance as your first guide. In other words, the number of steps away from an exact match between the new member of your project and the modal haplotype. And for those members who are probably or only possibly related, use the time predictor tool as your second guide. And what I've done in the Farrell project, and I think it worked quite well, certainly when you're setting up a project in the early stage, it's to separate a core group from a peripheral group. And I did this with genetic family 2 in the Farrell project, and initially I divided them between 2A and 2B. As I became familiar with the genetic signature of those groups, and as I looked at new ways of seeing if they were related, including the matches ternal SNP analysis, then I was relatively confidently able to amalgamate the two groups into just one group. But I think initially when you're starting out with a Surname DNA project, it is quite a nice idea, I think, to have a core group who are all relatively close to the modal haplotype, and a peripheral group who are those people a little bit further away, maybe a distance of 4 out of 37, maybe even 5 out of 37, whom you're not entirely sure at this stage if they actually do belong in the project. Here's the Farrell DNA project, just to give you an example of this, and you don't need to look at the details so much, but the grouping was based solely on genetic distance. So I grouped people together on a basis of a genetic distance of 0, 1, or 2 out of 37, occasionally 3 out of 37, and very occasionally 4 out of 37. So most of these people were grouped based on a genetic distance of 0, 1, 2 out of 37. And this is what we found. The surname, the group 1 had the same surname variant, Farley, 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 Farley. So 5 Farleys out of 7 members altogether. Similarly, in genetic family 2A, they all had the same variant, Farrell, 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 and that was genetic family 2A. The other thing was that in genetic family 3, they all had the same location for the most distant known ancestor, Boat Court County, Virginia, in all 3 cases, and also they actually had the same name for their most distant known ancestor. And these people do not know how they are related to each other, but it just goes to show that based solely on genetic distance, we were able to also find other markers of potential relatedness that supported our grouping of these people together in each of these specific genetic clusters. And so we can tick off some of the markers of potential relatedness that we've explored so far. The member has the same surname, tick. The genetic distance between two members indicates a very close or very relationship. Tick. The same surname variant is predominant in a genetic group. Farley, Farley, Farley. The same MDKA location, Boatcourt County, Virginia, and the same MDKA, Gabrielle Farrell, in those three members of group number 3. So those are the first markers of potential relatedness. Now back to the admin pages, and let's look specifically at genetic distance, because this forms the basis of a lot of the work that you'll do as project administrators. And in this example here, we have the kit numbers of the various projects here. We're comparing at the DNA 37 level. Do remember to click that so to make sure you're comparing at the right level. Here we have the names of the individuals in the project, and you can see that there are 4 people who are ungrouped. So I have to group these people into specific projects. And to do that, first of all, I see what the genetic distance is by clicking on that particular arrow. And you have to click on the arrow to get to this screen. And it shows that, it says that for Mr. Wall, this is the genetic distance analysis that Mr. Wall has compared to each of these people at the 37 marker level. Now it also tells you what number of markers each of these people have tested. Do not confuse that with the level that you're comparing at. This is just the 37 marker level, but this tells you that if you wanted to go up to 67, you'd be able to compare this individual here, this individual here, and this individual here. 3 people have upgraded to 67, and you can compare at that level. Now this is the distance. So we have 5, 5, 6, 7, and 12. So Mr. Wall, his distance from all of these individuals here is 5, 5, 6, 7, and 12. His closest matches are outside the threshold, so they're all less than 4 out of 37. They're all greater than 4 out of 37, sorry, I should say, which means that none of these people are going to appear in his list of matches. They will appear in the Surname Project, but not in his individual matches list. Question is, of course, they are all members of the same group, and we can see it here, I2B1, genetic family 1. Question is he too a member of this group, or is he not related to them at all? The other thing we can notice here is that there is a clear demarcation between the first 4 matches, 5, 5, 6, 7, and the 5th match, which is 12. So it jumps from 7 out of 37 to 12 out of 37. So that's an interesting demarcation there, and we'll look at that again later on. Now, the biggest criticisms of genetic distance include that it does not take differing mutation rates into account. Because the different markers, some of them are fast mutating, some of them are slow mutating. Genetic distance does not take the differing mutation rates into account. Also, the thresholds are rather arbitrary. Should it be 4 out of 37? Should it be 5 or 6 out of 37? The reason for choosing a threshold is to try to limit the number of false positives that you bring into the project, and also to try and maximize the number of true positives that are actually allocated to a specific genetic cluster within your project. But it's arbitrary, and there's going to be a certain amount of casualties that fall by the wayside. So we need to bear this in mind. It is not set in stone. It could just as easily be 5 out of 37, and you might get very, very similar results, or even better results. It could be 6 out of 37, you could get worse results. But we need to bear in mind that this is a problem. The other problem, of course, with genetic distance is that it is subject to convergence, and that is something we'll look at in a while. Here is how you access the tip report, and this is something that we'll look at shortly as well. So, first of all, let's look at convergence. Is it a spanner in the wheel? Is it a red herring? Or is it perhaps both? Now, by convergence, and here's an example based on a single STR marker. So if you imagine that a single STR marker had a value of 8 10,000 years ago in the common ancestor to a group of people, and then over the course of time some of his sons mutated away from that value of 8, so that by the end of up to the present day, it now is a value of 11, or 13 rather. That would be an indication that there was a persistent forward mutation throughout time. Some other lines may not have diverged that much. Some others might have diverged in a downward direction and then converged up again towards the original value. This is an example of divergence. This is an example of lack of divergence. There's only one mutation from 8 up to 9, and then it stayed that way over the millennia. This is an example of convergence, where the green line has diverged away initially and then converged back towards the original value, and then has converged on the blue line, so that they both look the same. There's also convergence here, back at 6,000 years ago, where the green line diverged, so did the purple line, but then there was a back mutation on the green line and it converged on the purple line. And it is these back mutations and parallel mutations that cause so much trouble when we're trying to decipher genetic distance. Here's a back mutation here. The mutation went from 14 back down to 13. Here's a back mutation here. The mutation went from a value of 5 to a value of 6. Here's a back mutation here. It goes to a value of 7. It goes to a value of 8. And this is a parallel mutation. So the value here was 8, but then it became 7. And that was in parallel to the mutation from 8 to 7 that we saw on the green line 1,000 years previously. This is another back mutation here. Another parallel mutation. It's in parallel to this mutation that we see in the red line several thousand years beforehand. This is a visualization of what actually happens with convergence over time, because we've just been looking at one single marker, but of course it's a whole group of markers that are changing, back mutations, parallel mutations. And what may happen is that two distinct branches initially mutate away from each other, but then mutate back towards each other, such that their marker values appear to be very similar. And the result of it is that two distantly related individuals appear much more closely related than they actually are. And this is due to the back mutations and the parallel mutations, which are essentially hidden to us when we're looking at our present day STR data from our volunteers. The genetic distance is perhaps 4 out of 37 for a lot of these people in these branches here, and the connection looks like it's less than 1,000 years ago, but in fact it is more than 10,000 years ago. And that is the big problem with convergence. And it happens even at the 111 marker match. And these are some slides from Alistair MacDonald's Stewart project. We have the High Stewarts here, the Stewarts of Bunkle here. These two individuals, they have a genetic distance of 6 out of 111. But this chap here, Henry Stewart and Earl Castle Stewart, have a genetic distance of 7 out of 111, and Paul and Henry have a genetic distance of 3. Now, the most recent common ancestor for all of these people was probably about 1230 AD, around about this time up here, and that makes them approximately 39th cousins. But a genetic distance of 3 out of 111 makes them, certainly on paper, a lot more closely related than they would appear. So, for example, if we look at the frequently asked question from Family Tree DNA about how should the genetic distance at 111 markers be interpreted, if we go down to 3 out of 111, there's a 50% chance that they're 5th cousins, and 90% chance that they're 9th cousins, when in actual fact they are 39th cousins. So 9th cousins would take you back to around about 1650 or so. 39th cousins take you back to 1230. So there is a good 400-year gap there between what is estimated on the basis of the DNA and what we know from their genealogical data. There's a higher risk of convergence at lower levels of testing, so 12 markers and at 25 markers you're going to see much more convergence than you will at 37, 67 and 111, but it is still can be present, as we've seen, at 111 markers. There are higher levels of genetic distance, higher levels of convergence the greater the genetic distance. So you're going to see much less convergence at genetic distance of 0 out of 37 and much higher at 4 out of 37. There's lots of matches at 37 or 67 or 111 markers. That implies that there probably is a high risk of convergence in that particular group of matches. And this would be one of the several reasons for upgrading from 37 to 67 or 111 markers. Convergence may also be present if there's many different surnames among your Y-DNA 37 matches, there's no particular pattern, and it also may be more common in certain haplogroups or certain subclades and not in others. So for example, the Western Atlantic modal haplotype or the Nile of the Nine Hostages M222 subclades, these might be more prone to convergence than other subclades, and we still need to do a lot more analysis on these various subclades to get an impression of how common convergence is in various subclades. It's also more of a problem when you don't share the same surname with your match. It can happen with same surname matches like the Stewarts, like we've seen, but if you have two people who match each other but they have completely different surnames, then it either means that there's a possible non-paternity event happening sometime maybe in the last 1,000 years. It could mean that there's a pre-surname match happening sometime in the last 1,000 to 3,000 years before the time that surnames were introduced. Or it could mean that this is an example of convergence, and that could be up to 10,000 years ago. So how do you distinguish these various scenarios from each other? And that's where we come to looking at other markers of potential relatedness. We'll be looking at the matches terminal SNP analysis, possibly upgrading to 67 or 111 markers, or even downstream SNP testing. So that's how you'd actually be able to distinguish between these three scenarios in situations where there is a close match but different surnames. How do you quantify convergence? That's an interesting question, and when we look at the matches terminal SNP analysis, I'll show you a handy little technique for doing just that. So there are obviously quite a lot of shortcomings with genetic distance. The question is, how do we overcome them? Is the TIP24 score to the rescue? Well, let's take a look at that. The TIP24 score, what is it? Well, it uses the TIP tool or the TIP report, the TIP calculator some people call it, and in this particular example we have got Y-DNA 37 markers comparing Mr. Wall and Mr. Spearin, and when we use the default settings it says in comparing Y-DNA 37 markers which show 5 mismatches, the probability that Mr. Wall and Mr. Spearin shared a common ancestor within the last 4 generations is 0.8, 8 generations 11.07, and we go down to 24 generations, it's 90%. So these TMRCA estimates, you have to realize, are wildly broad, and they are of minimal genealogical value. They do not say approximately 130 years ago, and you can say, oh well, that would be at 3 generations ago, so that would probably be the level of my great-grandfather. Very, very unlikely that you can say that, because there are very, very broad confidence intervals on either side of these estimates, and the word estimate is a very important word here. The TIP24 score is when you compare Y-DNA 37 marker results using the default settings, so display it every 4 generations and don't fiddle around with it. That they do not share a common ancestor more recently than 1 generation, just leave that as it is. And you're looking particularly at the 24 generation value, and the value here is 90%. Now we're not interested really when we're using this TIP24 score, we're not interested in the TMRCA, the time to most recent common ancestor. We're not interested in generations, we're not interested in years. We're actually just interested in this percentage down here, because the TIP report takes into account, to an extent, the rate of back mutations and parallel mutations that one would expect to see in the STR markers, and in this particular example in the Y-DNA 37 STR markers. Now, we don't actually know how they do this because it's proprietary information that has not been shared, but the theory behind this is that it gives you a little better feel for how close two people are related when the genetic distance might be borderline, say 4, 5, 6 out of 37. And because it takes into account the varying mutation rates, it's possibly a lot more reliable than just looking at pure genetic distance. The only problem with TIP24 is that it does depend on genetic distance for its calculation, and therefore it is not a completely independent marker. It does depend on genetic distance, and I'll tell you why that's important later on. So it's only of interest for determining the closeness of the relationship between the various project members. And a question that remains to be judged by you as a project member, a project administrator, is what's the threshold you would set for including somebody in the same genetic family? Would you have a TIP24 score of 90%, of 60%, or somewhere in between? That's a question. Now, James Irvin has used this extensively in his Irwin DNA project, and he uses a cutoff of 80%. And you can see here that a TIP score of 80% to 100% will cluster people nicely in the projects. But it could be, for your own particular uses, it could be lower than that, it could be down as far as 60. And I would always compare the new members to the member closest to the ancestral modal haplotype in order to avoid genetic distance creep. And I have a question mark there because, like I said earlier, we don't tend to use the term ancestral modal haplotype anymore, just modal haplotype for the group, because we've no guarantee it is the ancestor's modal haplotype. Secondly, the modal haplotype for the group may be skewed, and we might be skewed more towards one particular distant branch descended from a particular ancestor than towards the ancestor himself. So we have to be careful about that as well. And there's also this possible problem with genetic distance creep, and we'll take a look at that now. So I just mentioned these issues so that you're aware of them and you can use your discretion when applying the TIP24 score. Now, here's the TIP24 score for a group of people here. And this first one has a TIP24 score of 90%, next one 90, next one 75, the next one 60. So which of these would actually be grouped together on the basis of the TIP24 score? Would it be these two with the 90% value, or if we are allowing a more lax one at 60, would we allow all four of them to go in? Well, if we look at the TIP report and the TIP24 score at the 67 marker level by clicking here, then we get these figures down here. 52%, 75%, 44%. So there's been a huge difference, a huge jump in these individuals comparing the TIP37 24 score and the TIP24 score at 67 markers. So again, it is difficult to rely very confidently on this particular marker of potential relatedness. It has the same limitations as genetic distance because it depends on genetic distance and therefore is not independent. So how often does this occur that we have a difference in TIP24 score between the 37 marker and 67 marker levels? SNP testing reveals different terminal SNPs, and of course that is the ultimate marker of potential relatedness, which we'll talk about later on. So a borderline TIP24 score, what do you do? Well, there is distinctly a risk of convergence here. You would have to assess other markers of potential relatedness first, looking particularly at rare marker values and the matches terminal SNP analysis. Consider upgrading to 67 markers, because that might give you a much clearer estimate of the TIP24 score than you would have at 37 markers. A genetic distance of 4 out of 37 markers may still be 4 at 67 markers, and therefore a much closer match may emerge. And then we should also consider SNP testing. So that's what you do with a borderline TIP24 score. Key message: look at other markers of potential relatedness. So there's the TIP24 score there. I'm only giving this an orange tick because I'm not as convinced about its utility as I have been previously. So that only gets an orange tick. Now, I mentioned genetic distance creep. What exactly does that mean? Well, I call this the admin's nightmare. So imagine, for example, you have two people in your project and they are related to each other with a genetic distance of 4 out of 37. Then another person joins the project and they are 3 out of 37. Another person joins, they're 2 out of 37 away from you as the starting member. Another one joins 2 out of 37, and another one joins 4 out of 37. All the people nicely grouped around you who happen to be the modal haplotype in this particular scenario. And another one joins, again, 4 out of 37. But then somebody else joins. They're actually 4 out of 37 to this person here, who was 4 out of 37 to you. So the genetic distance there is 8 out of 37. And then another person joins, and the genetic distance to you is again 8. And then another person, 12, and another person, 12, and another person, oh my gosh, what's happening? Leave my genetic cluster alone, because suddenly the core group has outliers with a genetic distance of up to 4, 8, 12, 16, 20, 24 steps out of 37 markers. Are all these people really related to each other? Do they belong in the same group? And this is why I say identify a core group from the modal haplotype with a genetic distance of 4 out of 37 and put the others near matches in a peripheral group for now. This is the way that I think it's a great idea to start a project. Just focus on those that are close to your own particular core group. You can always add in members from the ungrouped section at a later point in time, once you've had a chance to look at other markers of potential relatedness. But does genetic distance creep occur in practice, or is this just a theoretical situation that doesn't actually occur in practice? Well, I looked at various genetic clusters in my Gleason and Farrell project. This is Gleason lineage 1, Gleason lineage 2, Farrell Group OR1b GF2 and OR1b GF6. And those are the numbers involved in each of the projects, 27, 19, 23 and 5. And I went through each of these 27 members in turn and I looked for the maximum genetic distance that each member had to the other members of the project. So for example, 9 people had a maximum genetic distance among their compared to other people in Gleason Group 1, a maximum distance of 9 out of 37. 10 people had a genetic distance of 5 out of 37. 4 people had a genetic distance of 6 out of 37, and 4 people had a genetic distance of 7 out of 37. That was Gleason 1. In Gleason 2, it was much more distant. The maximum genetic distance between members, 4 members had a genetic distance of 7 out of 37, 12 a genetic distance of 8, 1 had 9, and 2 members had a genetic distance of 10 out of 37 markers, which really is quite distant. But look at the Farrell 2 group. They had 1 member with a GD of 9 out of 37, 7 with 10, 6 with 11, and they even had 2 with a genetic distance of 15 out of 37 markers. And in the Farrell Group 6, there was again 1, 1, 1, 2 people with a genetic distance of 10 out of 37. So there was a degree of creep, but it didn't get up as far as 24 out of 37. And the maximum that I've seen in my projects has been 15 out of 37, and that was in Farrell Group 2. And partly it's explained if you look at the age, or the estimated age of these various projects. So for example, in Gleason Group 1, all of these people go back to Thomas Gleason from Cockfield, Suffolk in 1610. So this particular group has a common ancestor that was born about 400 years ago. So it's a relatively young group. If you look at Gleason 2, the time to most recent common ancestor was about the time to the common ancestor was about 1200 AD, based on our current calculations. And if you look at Farrell Groups 2 and 6, we're looking at some time point prior to 1300 AD. So that possibly gives you some indication of why there is this increased amount of maximum genetic distance values in the Farrell 2 group, because perhaps that particular group has been around for a long, long time, and because it's been around for a long, long time, it has undergone a lot more mutation away from the modal haplotype than any of the other groups in this particular example. So that would be one explanation for what we're seeing here. The maximum genetic distance creep is 15 out of 37. You can express that as a percentage just to give you some idea of how large that genetic distance creep actually is. And in this example, we have a genetic distance creep of 41% for the Farrell 2 group. And the percent doesn't mean anything, it's just a way of expressing it. Similarly, at 67 markers, we're seeing again a spread. The maximum genetic distance creep here is 11 out of 67 markers, and we have 6 people in Gleason Group 2 and 1 person in Farrell Group 2 with that particular genetic distance. There are far fewer numbers tested out to 67 markers, so it is not as comprehensive an analysis as you see at 37. And then at 111, even fewer people, and the maximum genetic distance creep we see there is 16 out of 111, which gives you a 14% value for your genetic distance creep in this particular example. So that's genetic distance creep. Not a particular problem in practice, but a lot of people out there, I'm sure, a lot of you project administrators will have considered this as a possibility, and it will have caused some consternation. And it will potentially stop you from adding the more distantly related people to a particular genetic cluster. So it might give you pause if you come across someone who is 5 or 6 out of 37. Should I really add them to the group, or should I leave them out? Genetic distance demarcation is the next topic I want to look at, and this is very useful because it's a very useful sense check of your grouping process. Gives you a good idea whether you are on the right track, and it also potentially identifies other members that might belong to specific genetic clusters. So let's take a look at this. I looked at the Maxwell DNA project a couple of months ago, and what I noticed was there was a clear demarcation. This is a 111 marker comparison. Clear demarcation between one group of people and another group of people. And similarly at Maxwell Group 2, there was again a clear demarcation. We had 12, 12, 12, 12, 12 here, and then 28, 32, 32. So a jump of about a jump of 16 points separating these two groups. And what I've found is that this genetic distance analysis, which you can do via your admin pages, click on genetic reports and then genetic distance, this genetic distance analysis, especially at 111 marker level, and there you see the number of markers up there, and also at the 67 marker level, often shows a clear demarcation between members in the same group and members in other groups within the project. Let's look at the Gleason Group 1, and here we see another clear demarcation. Here is lineage 1 here, the rest of them are not lineage 1. So very clear demarcation here. The genetic distance jumps from 7 out of 111 to 36 out of 111, clearly demarcating these two groups, and strongly suggesting that they have been accurately grouped together. Again, at the 67 marker level, a clear demarcation between 6 and 23. Here are the lineage 1 groups, lineage 1 members here, and below that demarcation there are members from a variety of different other groups. The genetic distance jumps from 6 out of 67 to 23 out of 67. Gleason Group 2 at the 67 marker level, again a clear demarcation down here. 9 out of 67 jumps up to 14 out of 67. All the lineage 2 members are clearly grouped here, and everything below that point of demarcation, they belong to other groups, other surnames, lineage unassigned, lineage 1, and so on. And we see that 2 of these people have a distance of 8 out of 67 and 9 out of 67. These, of course, will not appear as matches for this particular individual, whoever we're testing for genetic distance. They won't appear in his list of matches because the threshold is 0 to 7 out of 67, and these are 8 or 9. Similarly, Farrell Group 1, 111 marker level comparison, clear demarcation, 6 out of 111 jumps to 31. All the people above the demarcation point belong to genetic family 1, all of those below belong to other groups. And Farrell Group 2 at the 67 marker level, again a clear demarcation, everybody above in genetic family 2b, everybody below in different groups. These particular individuals here, 8, 8, 9, 9, these will not appear in this individual's matches, the one that we're testing, because the cutoff is 7, and these are above that particular cutoff. And then the 37 marker level, we're still looking at Farrell Group 2. There is a clear, well, demarcation is not clear. These are all the people in Group 2b. They are demarcated here, but there is no demarcation in terms of genetic distance. It goes 6, 6, 7, 7, 7, 7, 8, 9, 10. So the 37 marker level in this instance does not give you a very, very good assessment of demarcation. The other thing, of course, is these people here, 5, 6, and 7 out of 37, will not appear as a match in this particular individual's match list because the threshold is 4 out of 37. Now, I used this when I came across this particular genetic distance demarcation technique when I was grouping new members into my Farrell DNA project. And here are one new member is compared to everybody else in the project, and quite clearly most of his close matches are genetic family 2b, 2b, but then there's some ungrouped people here, and then 2b, 2b again, and then 3 more ungrouped, and then genetic family 5. So if there was to be a demarcation between the various groups, between 2b and all other groups, where would it occur? Well, the genetic distance doesn't give us any real clue because it's 9, 9, 10, 10, 10, 10. There's 13. Maybe it's around about here. But what I did was I looked at these 1, 2, 3, 4, 5 ungrouped members and assessed their DNA to see if there were any other markers of potential relatedness. And in particular, I was looking at their matches terminal SNP analysis, and here's what I found. This one did belong in genetic family 2b. This one was borderline. This one belonged in genetic family 2b. This one belonged in genetic family 2b, and the one with a distance of 13 out of 37 did not belong in genetic family 2b. And that was on the basis of the assessment of other markers of potential relatedness in those specific individuals who appeared in this genetic distance analysis because they were relatively close to the new member and possibly closer than other members of the group. But it led me on to a very interesting analysis of all of the people in my ungrouped section of the project, and it was as a result of my analysis 4 additional people. These 4 people here, including this borderline case, I've added them to Genetic Family 2. So if you want to read about it, the link is there, and it was a very interesting exercise. So to summarize genetic distance demarcation, demarcation of genetic distance at 67 and 111 markers suggests which project members belong in group X and which do not. And it's a very useful sense check that your grouping is in fact correct. And furthermore, it can help identify outliers that should possibly be moved from your ungrouped section into a specific genetic cluster, a specific group X within your project. But it will be necessary to assess these potential candidates for other markers of potential relatedness in order to decide. And there again is the link to that blog post on that particular exercise. So coming back to our markers of potential relatedness, we now have ticked off number 4. There is a clear genetic distance demarcation between project members within a genetic cluster and project members outside it. What are we going to look at next? Rare marker values. Are they specific for certain genetic families? Well, the wonderful Leo Little created a spreadsheet quite some time ago, and it never really has been updated since then. And we desperately need it, because this only addresses some of the most common haplogroups within genetic genealogy. We see E3A, E3B, haplogroup G, I, J2, OR1A, and importantly OR1B. And what it does is it looks at each marker, or locus in turn. These are the STR markers. Here's marker 390, here's marker 19. It tells you how many people were assessed for each of these markers, and then it gives you how frequent each of these values are in each haplogroup. So in haplogroup OR1B, this particular marker 393 occurs at a frequency of 4%. The value of 12 for this marker occurs at a frequency of 4%, the value of 13 at a value of 91%, the value of 14 at a value of 5%, and the value of 15 at a value of less than 0.0 something percent. So that would be certainly a rare marker value. Anything less than 5% probably would be considered a rare marker value, but that's another definition that is really quite arbitrary, So this has the frequencies of each of the 67 STR marker values for those 6 haplogroups you see there. But it would be nice to have these type of frequencies for a lot more haplogroups and for a lot of the major subclades. For that kind of information, you probably have to go to the haplogroup project administrators. Some of them may have some information published for a particular subclade. So, like I say, the definition of a rare marker value is open to questions. James Irvine suggests a frequency of less than 5%, and I think that's a very reasonable suggestion. The term rare means the markers that stand out from the rest of the group. These may be single rare values, or they may be several rare marker values within a particular genetic cluster. Some administrators say they are very predictive of grouping, and they may even be in the first 12 markers. And in the case with Kelly Wheaton, which we'll see, a Y-DNA12 test may be enough to classify people on the basis of their rare marker values within those 12 markers. So here's the Farrell DNA project again, grouped, as I said, purely on the basis of genetic distance, 0, 1, 2, 3, 4 out of 37. And what we find is that in group 3, there is a rare marker value of 26 in DIS 449. And there's DIS 449 there, and you can see there's the value of 26 in group 3. None of the other groups have this value. And when we look at Leo Little's spreadsheet, it says it occurs in only 1.7% of the general population, but in 0% of OR1b. So this is very rare, and as a further pointer or further confirmation, further supportive evidence of the relatedness of these individuals in this particular group. They all share the same rare marker value. Here's an example from Kelly Wheaton's project, and we're looking specifically at Wheaton Group B. And here, for marker 393, the value in, there's Group B there, there's Group C. Here's the value in Group B, it's 5%. In Group C, it's 91%. So we could say that a value of 14 for marker 393 in Group B is a rare marker value, and that's in Group B. 390, the frequency is 60% in Group B and C. The value is 24, 23, 24, and 25, and it occurs in 22%, 60%, and 16%. In Group B, it's 24. In Group C, it's 24. For STR marker 19, in Group B, it occurs, the value is 16, which occurs in only 1% of the population. Again, a rare marker value. In Group C, the value is 14, which occurs in 89% of the population. So that's not a rare marker value. If we come down to the next one, we see that in Group B, the value is 11, which occurs in 67% of the population, and it's 12 in Group C, which occurs in 4% of the population. Again, that would be a rare marker value. Marker 385A, in Group B, the value is 12, and that occurs in 8% of the population. In Group C, the value is 11, which occurs in 85%, therefore it's not rare. So if we look at Group B, we see there are three relatively rare. 8% is a little bit higher than you'd want for rare, but it's still low nonetheless. And the probability of all three of them occurring in the same sequence is around about 1 in 62,000. So on the basis of these first 5 markers, Kelly can be reasonably confident, and when I say reasonably confident, I mean 99.9% confident, that these people belong to Group B. With Group C, the probability of this sequence occurring in the general population is around about 1 in 61. Excuse me, so it's not really the same thing. They are not predictive for Group C, but these first 5 markers certainly are predictive for Group B. And in this case, the Y-DNA 12 marker test is sufficient to allocate some members to Group B. It's also very important to join haplogroup and geographic projects and to encourage your project members to do so, because they have SNP testing data, because they have a much broader overview of the STR data than you will have as a Surname Project Administrator. And when I was recently in conversation with some project administrators for the Z253 project, they were able to point out to me that there was a connection between the Farrells and the Harrells. And that proved to be very, very true. We found other evidence to confirm and support that they are in fact related to each other, and the branching point would have been sometime back in the 1600s. But this was something that I would have missed completely because I did not have Harrell as a surname in my Farrell DNA project, and it was only the oversight of the haplogroup project administrator who was able to notice a genetic pattern, was able to put 2 and 2 together, and was able to get in touch with me. So do have a close relationship with all of the haplogroup project administrators for each of the terminal SNPs you're able to identify in each of the genetic groups within your surname project. So that's rare marker values ticked off. The last 2 then are totally associated with SNP predictions and SNP testing. If you're looking at SNP testing, then the terminal SNP must be consistent within a given group. You can't have some members of the group testing for haplogroup, or testing for one DNA marker, for example M222, and the other is testing for some other very distant DNA marker, say U106. This would actually place them on entirely different branches of the human evolutionary tree, and it would make no sense to group them together at all. So SNP testing is the ultimate arbiter of whether or not people should be grouped together. It establishes the terminal SNP, or rather the current most downstream SNP, because terminal SNP has an element of finality about it that I don't particularly like, and it is a little bit of a misnomer. The only reason that you have a terminal SNP at the moment is because no other SNPs downstream have been detected, or because you haven't tested for SNPs that are downstream. So I would say to use the term the current most downstream SNP rather than the term terminal SNP. And why do we do SNP testing, or why might you do SNP testing? Firstly, to place individuals more downstream on the haplotree. So upstream is back towards Africa, back in the past, 10, 20,000 years ago, 50,000 years ago. That's all upstream. Downstream is closer to the present day. You can also do SNP testing to assist with difficulties in grouping, like we've said, and this also helps reduce the possibility of convergence, certainly of upstream convergence. You may still get a degree of downstream convergence depending on how far downstream you test, but it certainly will put you a lot more in the ballpark of where you want to be. Information on deep ancestry and possibly geographical origins. This will be something that will be of interest to some people. And also to help identify branches within a genetic family and to build mutation history trees, and that's a separate presentation all on its own. But certainly haplogroup and geographic project administrators will be interested in the investigation of deep ancestry and possible geographical origins. So that would be another reason for doing SNP testing, would be to support your local haplogroup project administrator. And there's various places that you can get these SNP tests from. You're probably quite familiar with these companies. Family Tree DNA have introduced some deep clade panel tests, which are quite useful, and I use them quite a lot. There are three types of SNP test. There's the single SNP, $39 at Family Tree DNA, $17.50 at YSeek. There are new SNP panels or packs from Family Tree DNA, usually $119. You can also get them from YSeek. Next generation sequence testing. The big Y costs $575 or $460 in the sale, and then Full Genome Core have the Y Elite, which is another option for NGS testing. These are expensive tests, so it might be useful, and I think in all cases it would be useful to do a matches terminal SNP analysis first, and even get advice from the haplogroup project administrators on which of these SNP tests should be undertaken. Now, we've talked about this previously, matches terminal SNP analysis. This is how you actually do it. You open the individual's matches list. So say you have a new project member, you want to group him, you open his matches list, his Y-DNA matches list, and you can go down to the 25 marker level. You know, you can start at 111, 67, 37, go down to 25, and sort the list of his matches by haplogroup by clicking on the heading. Note down the terminal SNPs of his matches and how often they occur, and then plot the SNPs on the haplotree, whether it's Family Tree DNA or YFull or wherever, to see whether they fall on the same branch or on different branches. If they fall on different branches, then you're looking for convergence. And this may be upstream convergence, where the branches are quite high up in the human evolutionary tree, or it might be downstream convergence, where the branches are actually adjacent and possibly indicating neighbors in the last several thousand years. And here's an example from the Farrell project. What I would do is, first of all, open the person's matches, go down to the 25 marker level, increase the page range so I get all 183 matches on the same page, and then I would click on Y-DNA haplogroup. And this arranges them all by the marker alphabetically. And I'd make a note of each marker and the frequency with which each one occurs. There's 2 there, there's 2 there, but here is 1, 2, 3, 4, 5, 6, 7, 8 occurrences of L1335. So where is L1335? Where are these other SNPs on the human evolutionary tree? What happens if you plot them on the tree? Do you get a nice single line, or are they scattered across various branches of the tree? Well, here is FTDNA's tree, and there is L1335 there. So now I know where it is, and it is a sub-branch of the one above, and that's a sub-branch of the one above, and I can go back and back and back, and I can put the SNP progression together, starting with or M269, or whatever the most upstream one is, and coming all the way down, noting the SNPs at each of the branching points of the tree along the way. And here's an example of one. There's the diagram and how the SNPs all fall on the same line, and this is the kind of output that I would get from a matches terminal SNP analysis, and I would include this in emails and send it to prospective or to the new members so they have an idea of what's going on. His 37 marker matches have the following terminal SNP markers: 1 occurrence of FGC 5659, 7 of 5628, and 7 of L226. A similar profile emerges when reviewing his 25 marker matches, with the addition of these ones here, and it gives an estimated SNP progression of, there's haplogroup R, 312, L21, all the way down L226. The ones in bold are the ones that we see among his matches. So the analysis identifies 5 SNPs, and when we plot these on the haplotree, there's the 5 SNPs in bold, plot them on the haplotree, there is no evidence of convergence. They are all on the same line, the same branch. It comes down here, and there's the next branch down there, and then down there, and then down here, and then down there. So that is described in the Birth of a New Genetic Family GF6 on the Farrell blog, and you can see the web link there. Here's another example. Again, all the yellow dots indicate SNPs that appeared in this individual's matches, and they all follow a very, very neat single line all the way down. There's no branching off onto other branches. There is no evidence of convergence. All his matches lie on one line only. Now here's an example of downstream convergence, and this goes from Z253. One of his matches had, one or several of his matches had Z253. One or several of his matches had L226. Some had FGC, I believe that is 5628. And then one of them, this is where it kind of split into 2 branches. One person had FGC 5659 down here, the other one had DC24. So these are separate branches of the haplotree, but they are adjacent to each other and relatively downstream. So what we can say here is that this is an example of downstream convergence. In this situation, what I was able to recommend to the individual was that he definitely lies below Z253, definitely below L226, and there is a new L226 SNP pack that is available in the near future, June or July of 2016. And it means that I'm able to recommend to this particular new project member with 99% confidence that he should do the L226 SNP pack, because there is a 99% chance that he will find that he lies on one of these branches below L226. And that saves him the cost of doing the M343 backbone panel test. First of all, I say forget that, bypass that, go straight to L226 on the basis of our matches terminal SNPs analysis. Here's an example of upstream convergence, and the yellow dots are his matches, and you can see that they are really spread out quite widely on the M22 portion of the big tree. And the red arrow is the predicted sub-branch based on his matches terminal SNP analysis. The green arrow is the actual sub-branch that he sat on. based on the M22 SNP pack test. So this is the kind of situation where you get the results and you're predicting something else. You start thinking, is there a lab error involved? It's always worthwhile checking with the lab to see if a mistake has been made, but it also points to the fact that in some subclades, and I think M222 may be particularly blameworthy in this regards, in certain subclades you will get a very large amount of upstream convergence, where you see that the SNP markers of an individual's matches are actually spread out quite widely on the human evolutionary tree. So, to summarize then, the matches terminal SNP analysis can be surprisingly predictive in many cases of which downstream SNP a particular new project member will test positive for. It works best at the 25 marker level purely because people have more matches at the 25 marker level and more people have tested SNPs. The more matches you have, the more people who have tested SNPs. The 37 marker level can work as well. So can the 67, so can the 111, but it very, very much depends on how many matches you have at a particular level. So I would confidently go down to the 25 marker level. I have even gone down to the 12 marker level with some success, but again, 25 would be my default rather than anything lower than that. It frequently identifies the most likely terminal SNP, and it can be followed by more focused confirmatory SNP testing, and therefore saving your project members money. It allows also an estimation of the amount of convergence in a particular project member's match list. So a new member joins the project, asks you the question, how many of my matches do you think are convergence? And how many of them are real matches to whom I'm related genealogically within a genealogical time frame? And this is how you do it. For example, one Farrell member's terminal SNP was FGC 20561, and this is described in the Farrell blog on that link there. And this is by a single SNP test. So this is somebody who is confirmed to have the terminal SNP FGC 20561. But we did a matches terminal SNP analysis on this particular individual, and this was the SNP marker progression that emerged. And the ones that we see there, L21, Z253, and then FGC 20561 occurred 5 times, FGC 20562, the adjacent branch, occurred twice. But it could also have been S845 going down to FGC 20563, which was also another adjacent branch, but a little bit more distant. There was evidence of convergence, particularly more downstream, based on this matches terminal SNP analysis and this estimated SNP progression here. Some of his matches SNPs appear on adjacent branches, such as these ones here. And of the 33 SNPs tested below the upstream SNP L21, this one here, at least 7 of these 33 are on adjacent branches. So he had 33 SNPs, 33 terminal SNPs tested below L21, and roughly, well, at least 7 of these were on adjacent branches, indicating convergence. So a very crude estimate of the degree of convergence among his 25 marker matches was 7 divided by 33, which is 21%. In other words, the amount of convergence seen among this particular individual's 25 marker matches was 21%. 21% of his matches were the victims of convergence. This will improve over time as more people SNP test, and more people at the 37 marker level will have SNP marker analysis, and there will be more matches at the 37 marker level. But for now, doing this calculation at the 25 marker level seems to be very predictive. Here are some resources for haplotrees and SNPs that I find particularly useful. FTDNA's haplotree identifies the SNPs that Family Tree DNA has named There may be different names on other trees, so if you're having trouble finding an FTDNA SNP on some other tree, look at the haplotree on FTDNA to see where it sits, so that you can maybe identify its position on the basis of the more upstream SNPs on that particular branch of the tree. Y-full has another haplotree. The advantage of Y-full's haplotree is that it actually gives the dates for each of the SNPs' age and tells you how long ago they were formed. The ISOG haplotree translates SNPs into the old long terminology, so it can be quite useful for that. I don't really use it for much else. And then the specialist subclade haplotrees, such as Alex Williamson's big tree for OR1b, and individual haplogroup projects, which may have their own haplotrees. These are very, very useful. They're usually kept up to date by the project administrators, and that's another reason for why we need to have very close ties with haplogroup project administrators. And lastly, Y-browse is very useful for finding SNP information, particularly if you cannot find a particular SNP. You can actually search for its name in Y-browse. Also, if there is a particular location for a SNP, but you don't have a name for that SNP, you can put the location into Y-browse and see if there are any other equivalent names for that particular location. Do join haplogroup projects. OR1b and subclades is essential for anybody who is in the OR1b group. Do join their mailing lists, their Facebook groups, their forum, so that you're kept abreast of what's happening in the haplogroup projects. The admins will group your project members according to their SDR values, signpost you to other subclade projects, identify rare or unique marker values within your particular group, and can advise on targeted SNP testing strategy. So it's important to collaborate and do this SNP testing strategy in collaboration with haplogroup project administrators. So those are the last two ticked off, number 6 and number 7, SNP predictions and SNP testing, and those are the markers of potential relatedness. I would have said back in June 2014 that a suggested approach to grouping people together, if you're a new Surname Project Administrator, is to use genetic distance as your first guide. And that's very, very useful just for getting a core group together. Then I said probably if you're looking at the probably related or only possibly related, use the TIP24 score compared to the modal haplotype for the group as your second guide. And then for those borderline cases, consider the TIP24 score, rare marker values, targeted SNP testing, and further documentary research. That was back in June 2014. In July 2016, I'm thinking more along the lines of yes, definitely use genetic distance as your first guide, but I would go for the matches terminal SNP analysis as your second guide, because I think it's very, very useful, and it avoids the problem with the TIP24 score, which was that it actually is dependent on genetic distance. So it's not an independent variable. It is dependent on genetic distance, and I think is subject to the same problems that we have with genetic distance. Whereas SNPs are completely separate from genetic distance using STRs, and therefore can be considered an independent variable that is a very useful second guide. Then I would go to rare marker values as a third line, and then for those that are still borderline, look at the genetic demarcation between your group and others. Does it give a clear indication? Using the TIP24 score at 37, 67 or 111 markers might be useful. You should consider upgrading that individual to 67 or 111 markers, or do targeted SNP testing as well as further documentary research. So what should you recommend your members do after their initial Y-DNA37 test? Should you consider upgrading to 67 or 111 markers? Or should you consider doing a single SNP test or a SNP pack or doing the big Y? Well, it all depends really, and in some situations you will do one, in some situations you'll do the other. in terms of upgrading to 67 or 111 markers, the time to do it is when there are no matches at 37 markers, or to assist with difficulties in subgrouping, or when you have lots of matches at 37 markers, and this helps to eliminate those that are due to convergence. It also is useful in order to identify sub-branches within a genetic family if you want to generate mutation history trees or phylograms, cladograms, that kind of thing. And if the two individuals, if the new member wants to see how closely and how more precisely how closely he's related to somebody else in the project, then it would be worthwhile advising both of them to consider upgrading to 67 or 111 markers. And this is for people who think they might be relatively closely related, fifth cousins or closer. So, to summarize then, markers of potential relatedness help us group people together who have similar genetic signatures. And we've looked at genetic distance, matches terminal SNP analysis, the rare marker values, genetic distance demarcation, the TIP24 score, and SNP testing. And the decision to put somebody in a particular group depends on the totality of the evidence, which in turn is dependent on your own judgment as a project administrator, which in turn is based on your own accumulating experience. So best of luck with your projects. I hope you have found this rather comprehensive video quite useful. Thank you.